All right. Part 2, for module 7. So comparison to other function. Broadcast versus scatter. MPI broadcast send data or send the same data to everyone, while MPI scatter takes a large data set, A, B, C, D, and send a different piece to each processors, to the available processors. And broadcast versus all-to-all operation. In MPI broadcast, only one process speaks. In MPI, to all, MPI all to all, every process send unique data to every other process. All right, so that are different. So practical example. So MPI scatter and MPI getter. So figure 1 shows scatter is shown, taking a sequence A, B, C, D from one process and later distributing it, while getter is shown collecting those pieces back into a single order sequence. Okay, for example, we got scenario like parallel array processing. Imagine you have 4 numbers, so you want to send one number to each of the processes. So have each process square its number and then collect the result back at the start. So this is the code, okay? So you can have this code and run in your machine. So we got so they put that data in A, B, C, D, in the array, So then run that. Okay. So this is another code which is continual code for that scenario. Okay, according to figure 1, initial state, P0 holds the sequence A, B, C, D. Okay, so represented as 2, 4, 6, and 8. So scatter. The system split the data, so P1 receive B, so the number of 4, and P2 receive C, the number of 6, and so on. So while gather, after the match is done, the value are pulled back into a single array on P0 in correct order. So this is a practical example because it demonstrates how to use the network to turn a single thread task into a parallel one. So we got another scenario, calculating the global maximum. Imagine each process is a sensor in a large factory. So normally it's not one, could be more, 1,000, 2,000 sensors. So each sensor records a temperature. To ensure safety, the root or P0 needs to find the highest temperature recorded across the entire factory to trigger an alarm if necessary. Okay, this is like civilian system. So here is another example using MPI reduce, where reduce as shown in figure 1 is taking data from all the process P0, P1, P2, and 3, and using some operator to combine them into a single result on the root process. Okay, try to imagine that. So this is the code that we're going to use, and then please check this, to show this, and whether this, I'm not sure that, because I request you to check this, what's the correct answer for this, just in order to print this, okay, you can try this, and also this one as well, and please check this code, this format, how to generate the, I think, the symbol of Celsius degree, something like that, okay. So distributed data, so each process starts with its own data point, A on P0, B on P1C, on P2D, on P3. So the operator, which is MPI sum, so add all value together. Then we got MPI max, find the highest value, and also MPI min, find the lowest value. So finally the result, your document shows the final result ending up on P0. This is why if rank 0 prints all the final answer in the code. So another way you can use that MPI or reduce. If your goal was every sensor to know the global maximum, not just P0, so you can use MPI reduce. Figure 1 shows all reduce operation where the result is sent back to all the processes A, B, C, D rather than just one. Okay. So these are the example, very straightforward, broadcast a value. So we got this and value and broadcast to all the existing process. So all processor receive the value broadcast from pre-process of zero. This is a simple example. Okay, scattering on array. Okay, like we got the data and then how we do scatter. Each process receive one element from data. Okay, these are for scattering, another for gathering result. So this one for gathering, okay, result in the array, and then this one for reduction. So process zero correct sequence ranks from all the processes. And then this one reduction operation. So we use MPI reduce from all to one, yeah. So process zero get the sum for all the ranks, okay. So perform benefit. So finally, through this, actually, yeah, so we can improve the efficiency through reduced communication overhead and scalability through optimize for the large scale system, simplicity, easier to read and maintain than many point-to-point operation. And next, use cases in parallel program. So basically, so for distributing data for all the parallel processing, and next collecting result from distributing computation, and synchronization data across all the nodes, and common pitfall, mismatch count and type, incorrect root rank, and finally for forgetting, yeah, that all processes must call the collective function. And finally, conclusion, so MPI collective communication provide powerful tool for parallel computing. So understanding when and how to use each function improve both the performance and also clarity of the parallel application. Okay, that's all for part 2, module 7.